What appears to human intuition as emptiness has repeatedly proven, throughout the history of physics, to be one of nature's most active states. The idea that the quantum vacuum is not empty but filled with fluctuating energy is not a poetic metaphor but a precise scientific conclusion drawn from decades of theoretical insight and experimental confirmation. To understand this, one must first abandon the classical image of space as a silent container, and instead accept that space itself is a physical entity governed by quantum laws. In this view, emptiness becomes a dynamic stage where energy constantly appears, vanishes, and reshapes reality at its most fundamental level. In everyday experience, a vacuum is understood simply as the absence of matter. Remove air from a container, and we say it is empty. Classical physics extended this idea to the universe itself, imagining space as a neutral background where particles and forces interact, but where space itself does nothing. This assumption worked well for centuries, explaining planetary motion, mechanics, and electromagnetism. Yet when scientists began probing the atomic and subatomic world, this comfortable picture started to fail. At very small scales, nature refused to behave like a quiet machine, and instead revealed an unavoidable restlessness. Quantum mechanics introduced a radical constraint on knowledge known as the uncertainty principle. This principle does not arise from technological limitations, but from the structure of reality itself. It states that certain pairs of physical properties, such as position and momentum, cannot both be precisely known at the same time. The more accurately one is determined, the less accurately the other can be known. This rule has profound consequences for the concept of emptiness. If a particle were truly at rest in an empty space, both its position and momentum would be fixed. Quantum theory forbids this situation. As a result, motion can never be entirely eliminated. From this insight emerges the concept of zero-point energy, the lowest possible energy that a quantum system can possess. Even when all removable energy is taken away, something remains. This residual energy is not optional. It is required by the laws of quantum mechanics. The quantum vacuum is the state in which all fields exist at their minimum energy, yet even in this state they continue to fluctuate. These fluctuations are not caused by external disturbances. They arise spontaneously from the quantum nature of fields themselves. Modern physics understands the universe as being composed not just of particles, but of fields that extend throughout space. The electromagnetic field, the electron field, and many others fill the universe entirely. Particles are simply localized excitations of these fields, much like waves forming on the surface of an ocean. When no particles are present, the fields do not disappear. They remain, vibrating at their lowest energy levels. These vibrations are the fluctuating energy of the quantum vacuum. One of the most striking aspects of these fluctuations is that they occur even in complete darkness and at absolute zero temperature. Absolute zero represents the lowest possible temperature, where classical motion should cease entirely. Yet quantum fields continue to fluctuate regardless of temperature. This means the vacuum is never calm. It is alive with activity, even when stripped of all matter and heat. Space itself is restless. The reality of vacuum fluctuations was once questioned because they seemed impossible to observe directly. How can one detect something that exists even in perfect emptiness? The answer came through subtle but powerful experiments that revealed measurable consequences of these fluctuations. One such phenomenon is the Casimir effect, which demonstrates that empty space can exert force. When two uncharged metal plates are placed extremely close together in a vacuum, they attract each other. This attraction does not come from magnetism, gravity, or any classical interaction. It arises because the quantum vacuum between the plates behaves differently from the vacuum outside them. The fluctuating energy of space itself creates pressure, proving that emptiness has physical properties. Another compelling demonstration comes from the behavior of atoms. According to classical physics, an electron orbiting a nucleus should lose energy and spiral inward until the atom collapses. This does not happen. Atoms are stable, and quantum fluctuations play a crucial role in that stability. The energy of the vacuum contributes to maintaining the balance that keeps electrons in their allowed states. Without this background energy, matter as we know it could not exist. Even light itself reveals the activity of the quantum vacuum. In quantum electrodynamics, the interaction between charged particles is influenced by virtual particles that briefly emerge from the vacuum. These particles are not directly observable, yet their effects can be measured with extraordinary precision. The magnetic moment of the electron, for example, matches theoretical predictions that include vacuum fluctuations to an astonishing degree of accuracy. This agreement is among the most precise confirmations of any scientific theory in history. The presence of fluctuating energy in empty space also reshapes our understanding of nothingness. Philosophically, nothing has long been imagined as the absence of being. Quantum physics challenges this idea at a fundamental level. The vacuum is not a void, but a sea of potential. Energy is continuously exchanged, constrained only by quantum rules. Even the act of defining nothing becomes problematic because there is no physical state in which absolutely nothing exists. On cosmic scales, the implications become even more profound. The energy of the quantum vacuum may influence the expansion of the universe itself. Observations show that the universe is expanding at an accelerating rate, driven by an unknown influence often referred to as dark energy. One of the leading explanations for dark energy is vacuum energy, the cumulative effect of quantum fluctuations spread across all of space. If this interpretation is correct, then the same restless energy present in microscopic emptiness is shaping the destiny of the entire cosmos. This idea introduces one of the greatest puzzles in modern physics. When scientists calculate the expected energy density of the quantum vacuum using known theories, the result is enormously larger than what astronomical observations suggest. The discrepancy between theory and observation is one of the largest known mismatches in science. This does not mean vacuum energy is imaginary. It means our understanding is incomplete. The problem highlights how deeply the concept of fluctuating emptiness is woven into the structure of reality, touching both the smallest particles and the largest cosmic scales. The quantum vacuum also blurs the boundary between existence and non-existence. Virtual particles that emerge from vacuum fluctuations do not behave like ordinary particles. They appear and disappear too quickly to be directly detected, yet they influence real processes. Forces between particles, shifts in energy levels, and even radioactive decay rates are affected by these fleeting events. Reality, at its foundation, is not composed solely of stable objects, but also of transient phenomena that exist only momentarily. This challenges human intuition, which evolved to navigate a world of solid objects and clear causes. In the quantum vacuum, cause and effect become less straightforward. Energy can fluctuate without an apparent source, as long as it obeys quantum constraints. This does not violate conservation laws. It reflects a deeper version of them, one that allows short-lived deviations as part of the fabric of space itself. The idea that emptiness is energetic also changes how scientists think about creation. If space naturally contains energy, then the emergence of particles and structure does not require something to come from absolute nothing. Instead, structure can arise from fluctuations within an already active vacuum. Some cosmological models suggest that the universe itself may have originated from a quantum fluctuation. While such ideas remain speculative, they are grounded in the proven reality that the vacuum is not inert. Importantly, this does not imply randomness without rules. Vacuum fluctuations follow strict mathematical laws. Their behavior can be predicted statistically and incorporated into precise equations. The apparent chaos of the quantum vacuum is governed by deep order. This combination of unpredictability and structure lies at the heart of quantum physics and defines how the universe operates at its most fundamental level. As experimental techniques advance, scientists continue to uncover new ways in which vacuum energy manifests itself. From ultrasensitive measurements of atomic transitions to experiments involving superconductors and nanotechnology, the influence of the quantum vacuum is becoming increasingly tangible. What was once a theoretical curiosity has become a practical consideration in cutting-edge research. In recognizing that the quantum vacuum is filled with fluctuating energy, science has overturned one of humanity's oldest assumptions. Emptiness is no longer empty. Space is no longer passive. At every point in the universe, invisible vibrations are occurring, shaping matter, forces, and cosmic evolution. This realization forces a profound shift in perspective. The universe is not built upon silence and stillness, but upon ceaseless motion hidden beneath the surface of what we perceive as nothing. This unseen activity is not a minor detail. It is a fundamental feature of reality itself, revealing that even in the deepest void, the universe is alive with energy. The idea that zero-point energy exists even at absolute, zero temperature forces a complete rethinking of what temperature, motion, and stillness truly mean in the physical universe. For centuries, temperature was understood as a measure of motion. The hotter an object, the more its particles move. The colder it becomes, the more that motion slows. From this perspective, absolute zero appeared to be the ultimate end point, a state where all motion stops and energy disappears. Classical physics encouraged this belief, presenting absolute zero as a silent boundary where nature finally becomes still. Quantum physics, however, reveals that this boundary is an illusion. Even at absolute zero, the universe refuses to be motionless. Absolute zero, defined as 0 Kelvin, represents the lowest temperature theoretically possible. At this point, all thermal energy is removed from a system. Thermal motion, which includes the random jiggling of atoms and molecules caused by heat, is eliminated. In classical terms, this should mean complete rest. Yet experiments and theory agree that particles still retain energy at this temperature. This remaining energy is zero-point energy, and it does not arise from heat, external forces, or environmental interactions. It is intrinsic to the quantum nature of matter and fields. The reason zero-point energy persists at absolute zero lies in the quantum description of particles and waves. In quantum mechanics, particles are not treated as tiny solid objects following precise paths. Instead, they are described by wave functions that represent probabilities. These wave functions cannot collapse into a perfectly defined state of zero motion. If a particle were to have exactly zero kinetic energy, its position and momentum would both be known with perfect precision. This situation is forbidden by the uncertainty principle, which places a fundamental limit on how precisely certain properties can be known simultaneously. As a consequence, particles must retain a minimum amount of motion, even in their lowest possible energy state. This motion is not random thermal movement, but quantum fluctuation. It is subtle, unavoidable, and deeply woven into the fabric of reality. Absolute zero removes thermal agitation, but it cannot remove the underlying quantum restlessness that defines existence at small scales. This principle applies not only to particles, but also to entire systems. Consider a simple quantum oscillator, a model often used to describe vibrations in atoms, molecules, and fields. In classical physics, such an oscillator could be completely at rest with zero energy. In quantum mechanics, the lowest energy state of the oscillator still has a non-zero value. This baseline energy is the zero-point energy of the system. No matter how much energy is removed, the oscillator never reaches complete stillness. This behavior is not theoretical speculation. It is experimentally confirmed. One of the clearest demonstrations comes from the study of solids at extremely low temperatures. As materials are cooled toward absolute zero, their atoms do not freeze into perfect immobility. Instead, they continue to vibrate slightly within their positions. These vibrations are not caused by heat, but by quantum effects. Even at temperatures close to absolute zero, materials exhibit properties that can only be explained by the presence of zero-point motion. Helium provides a striking example. Unlike most substances, helium does not solidify under normal pressure, even at temperatures approaching absolute zero. Classical physics cannot explain this behavior. Quantum mechanics can. The zero-point motion of helium atoms is so strong that it prevents them from locking into a solid lattice. The atoms continue to move, driven not by heat, but by quantum energy that cannot be removed. The persistence of energy at absolute zero also applies to electromagnetic fields. Even in complete darkness, with no light present and no thermal radiation, the electromagnetic field still fluctuates. These fluctuations are a manifestation of zero-point energy. They exist regardless of temperature and cannot be eliminated. This means that space itself contains energy even when cooled as much as physically possible. This realization has profound implications for how energy is defined. Energy is no longer something that can be completely extracted from a system. There is always a lowest limit, a floor below which energy cannot be reduced. This challenges classical notions of efficiency, cooling, and control. No machine, no matter how advanced, can remove zero-point energy from a system entirely. It is not accessible in the same way thermal energy is, but it is always present. The existence of zero-point energy at absolute zero also explains why certain quantum effects remain active at ultra-low temperatures. Superconductivity, superfluidity, and other exotic states of matter emerge when thermal noise is minimized, allowing quantum behavior to dominate. In these states, zero-point energy plays a central role. It shapes how particles interact, how currents flow without resistance, and how fluids move without viscosity. These phenomena are not suppressed by the absence of heat. Instead, they are revealed by it. At absolute zero, the universe does not shut down. It reveals its most fundamental character. Without thermal distractions, quantum effects become more visible and more influential. The persistence of zero-point energy ensures that nature remains dynamic, even in its coldest possible state. Stillness, in the absolute sense, does not exist. This challenges intuitive ideas about coldness and emptiness. Cold does not mean inactive, and zero does not mean nothing. Absolute zero is not a state of nothingness, but a state of pure quantum behavior. What remains when heat is removed is not silence, but a quiet hum of quantum motion, subtle yet powerful. The implications extend beyond laboratory physics. In the vast cold regions of space, where temperatures approach just a few degrees above absolute zero, zero-point energy still dominates. Interstellar space, often imagined as frozen and lifeless, is permeated by quantum fields that never rest. Even in the deepest cosmic voids, energy persists. Space is never truly cold in the sense of being inert. It is always alive with quantum activity. This has important consequences for cosmology. The early universe passed through extremely hot phases, but as it expanded and cooled, it did not approach a state of zero energy. Even in its coldest theoretical future, quantum energy will remain. This suggests that the universe can never fade into complete inactivity. There will always be motion at the most fundamental level. The persistence of zero-point energy also reshapes discussions about the ultimate limits of technology. Cooling techniques have become extraordinarily advanced, allowing scientists to reach temperatures within billionths of a degree above absolute zero. Yet no experiment has ever reached absolute zero itself, nor can it. One reason is practical, but another is fundamental. Removing the final traces of energy would require violating quantum laws. Zero-point energy sets a hard boundary that cannot be crossed. This boundary has philosophical implications as well. For much of human thought, nothingness was seen as the absence of all properties. Quantum physics suggests that such a state may not be physically meaningful. Even when everything that can be removed is removed, something remains. This something is not matter, not heat, not light, but energy embedded in the structure of reality itself. The existence of zero-point energy at absolute zero also influences how scientists understand measurement. Any attempt to measure a system at ultra-low temperatures must account for quantum fluctuations. Instruments themselves are affected by zero-point motion. Absolute precision becomes impossible, not because of human limitations, but because the universe does not allow it. This understanding also explains why energy cannot be perfectly isolated. No system can be completely cut off from the quantum vacuum. Even in isolation, interactions with vacuum fluctuations persist. This ensures that absolute stillness is unattainable and that nature always retains a degree of unpredictability. Importantly, zero-point energy does not violate conservation laws. Energy is conserved globally, but quantum mechanics allows temporary fluctuations as long as they occur within strict limits. These fluctuations are not free energy in a classical sense, but they are real and measurable. They define the baseline from which all other physical processes emerge. As research continues, the study of systems near absolute zero remains one of the most revealing areas of physics. By stripping away thermal effects, scientists can observe quantum behavior in its purest form. What they consistently find is not emptiness, but structure, motion, and energy that cannot be removed. The existence of zero-point energy at absolute zero ultimately teaches a profound lesson about reality. The universe is not built on the absence of motion, but on its inevitability. Even when all heat is gone, when temperature reaches its theoretical minimum, the cosmos continues to vibrate quietly. This silent motion is not an imperfection or a leftover detail. It is a fundamental feature of nature. Absolute zero, once imagined as the endpoint of energy, is instead a doorway into the deepest level of physical law. It reveals that motion is not merely a result of heat or force, but a basic requirement of existence itself. Zero-point energy ensures that the universe never truly rests, reminding us that even at the coldest possible limit, reality remains alive with subtle, invisible motion. The idea that invisible quantum vibrations shape matter, forces, and the structure of the cosmos is one of the most transformative insights of modern physics. It suggests that the solid, stable world humans experience is not built from still components, but from ceaseless motion occurring at scales far beyond direct perception. What appears firm and permanent is, at its foundation, sustained by restless activity, tiny oscillations, fluctuations, and vibrations that never stop. These quantum motions are not side effects or background noise. They are the very mechanisms through which reality takes form. At the smallest scales, matter itself is defined by vibration. In quantum theory, particles are not rigid objects, but excitations of underlying fields. An electron, for example, is not a miniature sphere traveling through space. It is a localized vibration of the electron field. The same is true for quarks, photons, and every other fundamental particle. Matter exists because fields vibrate in specific, stable patterns. Without these vibrations, there would be no particles, no atoms, and no material world. This understanding replaces the classical picture of the universe as a collection of objects interacting across empty space. Instead, the universe is a continuous fabric of fields, each capable of vibrating in countless ways. What humans call particles are simply the smallest units of these vibrations. The properties of matter, mass, charge, spin, emerge from how these fields vibrate and interact. Matter is not something added to space. It is something space itself is doing. Quantum vibrations also shape the forces that govern nature. Forces are not transmitted by invisible strings or mysterious actions at a distance. They arise from the exchange of vibrational energy within fields. The electromagnetic force, for instance, is mediated by photons, which are vibrations of the electromagnetic field. When two charged particles repel or attract each other, they do so by exchanging these vibrational disturbances. What feels like a force is, at its core, a conversation of quantum oscillations. Even forces that seem static are rooted in motion. The repulsion you feel when pressing your hand against a table is not caused by solid matter pushing back in a classical sense. It arises from electromagnetic interactions between atoms, governed by quantum vibrations and the exclusion principles that dictate how these vibrations can overlap. Solidity itself is an illusion created by dynamic balance. The table feels solid not because it is motionless, but because countless quantum interactions are happening continuously and consistently. The structure of atoms provides a powerful illustration of this principle. Electrons do not orbit nuclei like planets around a star. Instead, they exist as standing wave patterns, stable vibrations determined by quantum rules. These patterns define the size and shape of atoms, the way they bond, and the chemistry that emerges from them. Change the vibrational patterns, and you change the nature of matter itself. The periodic table is, in a sense, a catalog of allowed quantum vibrations. Chemical bonds are also expressions of shared vibration. When atoms form molecules, their electron wave functions merge into collective patterns. These shared vibrations determine whether a molecule is stable, reactive, rigid, or flexible. Life itself depends on the precise vibrational behavior of molecules. Proteins fold because of quantum interactions that guide their structure. DNA maintains its shape and function because of forces rooted in quantum-level vibrations. Biology, often thought of as separate from physics, rests directly upon these invisible motions. Beyond matter and forces, quantum vibrations also shape space and time on the largest scales. The vacuum of space is not empty but filled with fluctuating fields. These fluctuations influence how particles move, how forces behave, and how the universe evolves. Even gravity, traditionally described as the curvature of spacetime, may be influenced by quantum vibrations, though a complete theory is still being developed. What is clear is that spacetime itself is not a static backdrop. It is dynamic, responsive, and possibly emergent from deeper quantum processes. The influence of invisible vibrations becomes especially evident when examining the early universe. In its infancy, the universe was extraordinarily small, hot, and dense. Tiny quantum fluctuations in energy were stretched by cosmic expansion, eventually becoming the seeds of galaxies and large-scale structure. The distribution of matter across billions of light years can be traced back to minute quantum vibrations that occurred in the universe's earliest moments. Entire clusters of galaxies owe their existence to fluctuations smaller than an atom. This connection between the smallest and largest scales reveals a profound unity in nature. Quantum vibrations do not remain confined to the microscopic world. Through processes like inflation and gravitational amplification, they can shape the structure of the cosmos. The patterns observed in the cosmic microwave background radiation are direct imprints of early quantum fluctuations. What began as invisible vibrations became the blueprint for stars, galaxies, and cosmic filaments. Even empty space between galaxies plays an active role. Vacuum fluctuations influence how light travels across vast distances, subtly affecting the behavior of particles and radiation. Over immense scales and long times, these small effects accumulate. The universe is not shaped solely by massive objects and dramatic events. It is continuously molded by quiet, persistent quantum activity. This perspective also changes how stability is understood. Stability does not come from the absence of motion, but from balance within motion. Atoms are stable because their internal vibrations settle into allowed patterns. Stars are stable for long periods because competing forces, rooted in quantum and classical physics, reach equilibrium. Even the universe itself may be stable or unstable depending on the behavior of vacuum energy and its underlying fluctuations. Stability is dynamic, not static. The invisible nature of these vibrations makes them difficult to grasp intuitively. Human senses evolved to detect large-scale motion, not fluctuations occurring trillions of times per second at subatomic distances. Yet technology has extended perception. Instruments can now detect the effects of quantum vibrations with astonishing precision. Atomic clocks rely on stable quantum oscillations to keep time with extraordinary accuracy. Lasers work by synchronizing the vibrations of countless atoms into a coherent beam. Modern electronics depend on quantum behavior within materials shaped by vibrational properties. Even silence is not silent at the quantum level. What humans perceive as stillness is a core, grained illusion. Beneath it lies continuous activity. This realization alters how emptiness, rest, and quiet are defined. There is no absolute rest frame where motion disappears entirely. There is only motion too subtle to notice without the right tools or theories. The shaping power of quantum vibrations also introduces limits. Because these fluctuations are inherent, they place boundaries on precision and control. Measurements cannot be infinitely exact because the systems being measured are always fluctuating. This is not a flaw of instruments, but a feature of reality. The universe resists being pinned down completely. It vibrates too much to allow perfect certainty. At the same time, these vibrations enable creativity in nature. Without quantum fluctuations, structures would not form, stars would not ignite, galaxies would not cluster, and complexity would not emerge. Fluctuations introduce variation, and variation allows structure to grow. The universe is creative because it is restless. This understanding also reframes the human place in the cosmos. Human bodies, thoughts, and technologies are all arrangements of quantum vibrations. The atoms in the brain fire signals through quantum, governed processes. The energy that powers life flows through molecular vibrations and electromagnetic interactions. Conscious experience emerges from systems built on these same invisible motions. Humanity is not separate from the quantum world. It is an expression of it. The phrase invisible cosmic vibrations is therefore not poetic exaggeration. It is an accurate description of how reality operates. From the smallest particle to the largest galaxy, vibration is fundamental. Matter is condensed vibration. Forces are exchanged vibration. Cosmic structure is amplified vibration. The universe is less like a static machine and more like a vast, intricate symphony, with each field playing its part according to quantum rules. Understanding this does not diminish the reality of the visible world. Tables remain solid, stars remain bright, and space remains vast. But it reveals that beneath these appearances lies a deeper layer of activity that never rests. Reality is not built from quiet foundations, but from constant motion hidden beneath the surface. As physics continues to advance, the role of quantum vibrations becomes ever more central. New theories seek to explain gravity itself as an emergent effect of deeper quantum processes. Experiments push the boundaries of control over quantum systems, revealing how vibration can be manipulated, entangled, and amplified. Each discovery reinforces the same message. Motion is fundamental, even where none seems to exist. The invisible vibrations that shape matter, forces, and cosmic structure remind us that the universe is profoundly dynamic. Stillness is an approximation, not a truth. What humans experience as a stable world is maintained by balance within perpetual motion. The cosmos, at every scale, is alive with vibration, quietly shaping everything that exists. For much of its early history, the idea that empty space could possess energy sounded like a mathematical curiosity rather than a physical reality. Vacuum energy emerged from equations, not from direct observation, and for a long time it remained an abstract consequence of quantum theory. Yet over the past century, experiment after experiment has transformed this idea into a concrete scientific fact. The vacuum is no longer a philosophical speculation or a theoretical convenience. It is a measurable, influential component of the physical world, and its effects can be observed, tested, and quantified with extraordinary precision. One of the most powerful ways science confirms the reality of a phenomenon is by demonstrating that it produces predictable, repeatable effects. Vacuum energy does exactly this. Although it cannot be seen directly, its influence appears whenever quantum systems interact with what seems, at first glance, to be empty space. These interactions leave unmistakable fingerprints in experiments, forcing physicists to accept that the vacuum is an active participant in nature, not an inert background. A turning point came with the realization that quantum theory does not merely describe particles, but fields that exist everywhere. When these fields are quantized, their lowest energy state is not zero. Instead, each field retains a baseline level of energy even in the absence of particles. Initially, this idea seemed untestable. How could one measure something that exists everywhere and cannot be turned off? The answer emerged not by isolating vacuum energy itself, but by observing how it alters the behavior of matter and radiation. One of the earliest confirmations appeared in the study of atomic spectra. When scientists measured the energy levels of electrons in atoms with extreme precision, they discovered tiny discrepancies between theoretical predictions and experimental results. These discrepancies were not random errors. They followed specific patterns that could not be explained by classical physics. The solution came from quantum electrodynamics, which showed that vacuum fluctuations slightly alter the electromagnetic field surrounding electrons. This interaction shifts the energy levels of atoms by a small but measurable amount. This phenomenon, known as the Lamb shift, provided direct evidence that the quantum vacuum affects atomic structure. The Lamb shift was revolutionary because it demonstrated that empty space modifies the properties of matter. Electrons behave differently not because of nearby particles, but because of interactions with vacuum fluctuations. When theoretical calculations that included vacuum energy matched experimental measurements with remarkable accuracy, skepticism faded. The vacuum was no longer invisible in practice. Its effects were embedded in the fine details of atomic behavior. Another striking confirmation came from the anomalous magnetic moment of the electron. According to simple theory, the electron's magnetic strength should have a specific value. Precision measurements, however, revealed a slight deviation. Quantum theory explained this deviation by accounting for interactions between the electron and virtual particles emerging from the vacuum. These fleeting entities briefly influence the electron before disappearing, leaving behind a measurable effect. The agreement between theory and experiment in this case is among the most precise in all of science, matching predictions to more than 10 decimal places. Such accuracy would be impossible if vacuum energy were merely a mathematical illusion. Perhaps the most dramatic and visually intuitive evidence of vacuum energy comes from the Casimir effect. This phenomenon arises when two uncharged, parallel metal plates are placed extremely close together in a vacuum. Classical physics predicts no force between them, yet experiments show that the plates attract each other. This attraction arises because vacuum fluctuations between the plates are restricted compared to those outside. The imbalance creates a pressure difference, pushing the plates together. What is remarkable is not just that the effect exists, but that its strength precisely matches theoretical predictions based on vacuum energy. The Casimir effect has been measured repeatedly, using different materials, geometries, and experimental techniques. Each time, the results confirm that empty space exerts force. This force is not due to hidden charges or external fields. It is a direct consequence of vacuum energy. In this case, emptiness behaves like a medium capable of producing mechanical effects. Space itself pushes and pulls. Beyond laboratory scale experiments, vacuum energy also influences how light behaves. In quantum electrodynamics, light traveling through a vacuum is subtly affected by fluctuations in the electromagnetic field. These fluctuations can polarize the vacuum, changing how photons propagate. Under extremely strong electromagnetic fields, the vacuum behaves like a nonlinear medium, altering the speed and direction of light in measurable ways. While these effects are tiny, advanced experiments and astrophysical observations continue to push the boundaries of their detection. Even the spontaneous emission of light by excited atoms reveals the influence of vacuum energy. An atom in an excited state will eventually emit a photon and transition to a lower energy state. Classical physics struggles to explain why this happens in complete darkness, with no external trigger. Quantum theory explains it by showing that vacuum fluctuations stimulate the emission. The atom interacts with the ever-present electromagnetic field of the vacuum, which nudges it toward releasing energy. Without vacuum fluctuations, spontaneous emission would not occur in the way it does. The vacuum actively participates in atomic transitions. In solid-state physics, vacuum energy also leaves its mark. The behavior of electrons in materials, especially at very small scales, is influenced by quantum fluctuations. Phenomena such as van der Waals forces, which cause neutral atoms and molecules to attract each other, arise from correlated vacuum-induced fluctuations in electric charge. These forces play a crucial role in chemistry, biology, and material science. They influence how molecules bind, how proteins fold, and how surfaces interact. Once again, effects attributed to vacuum energy appear in systems that shape everyday reality. At larger scales, experimental evidence becomes more indirect but no less compelling. Observations of the universe reveal that space itself seems to possess energy. The accelerated expansion of the cosmos suggests the presence of a pervasive influence acting against gravity. While the precise nature of this influence remains under investigation, one leading explanation is vacuum energy distributed throughout space. This interpretation aligns with quantum theory's prediction that empty space contains energy, even if the exact magnitude remains puzzling. The challenge here is not whether vacuum energy exists, but why its observed effects are so much smaller than naive theoretical estimates. This mismatch is one of the deepest mysteries in physics, but it does not undermine the reality of vacuum energy itself. On the contrary, the problem exists precisely because vacuum energy is real and must be accounted for. Observations demand an explanation, and vacuum energy remains central to that effort. Experimental evidence has also shown that vacuum energy cannot be ignored in advanced technologies. Devices operating at the quantum scale must account for fluctuations that arise from the vacuum. Quantum sensors, ultra-precise clocks, and superconducting circuits all interact with vacuum noise. Engineers and physicists design around these effects, treating them not as theoretical curiosities, but as practical constraints and tools. Importantly, vacuum energy behaves consistently across different experimental contexts. Whether measured through atomic shifts, mechanical forces, electromagnetic interactions, or cosmological observations, its effects follow the same underlying principles. This coherence strengthens confidence in its reality. Independent lines of evidence converge on the same conclusion: empty space is physically active. The cumulative weight of these experiments has reshaped how physicists define reality. Reality is no longer limited to what can be seen or touched. It includes fields fluctuations, and energies that manifest only through their influence on observable systems. Vacuum energy exemplifies this shift. It is not directly observable, yet its consequences are undeniable. This understanding also alters the role of experimentation itself. Experiments no longer merely test objects placed within space. They test space itself. When scientists measure forces, energies, and transitions, they are often probing the properties of the vacuum. Space becomes an object of study rather than a neutral setting. What makes this realization especially powerful is its inevitability. Vacuum energy was not invented to explain a single anomaly. It emerged naturally from quantum theory and was later confirmed across a wide range of experiments. Each confirmation reinforced the others, building a network of evidence too strong to dismiss. The vacuum revealed itself not through one dramatic discovery, but through persistent, consistent influence. In this sense, vacuum energy represents a triumph of modern physics. It shows how abstract mathematics, when combined with careful experimentation, can reveal hidden layers of reality. It demonstrates that even concepts that challenge intuition can be grounded in empirical evidence. The vacuum, once thought empty and irrelevant, has become one of the most important players in the physical universe. The experimental proof of vacuum energy's effects carries a deeper message. It reminds us that nature does not conform to human expectations of simplicity or stillness. The universe is active even where it appears quiet. Emptiness is structured, energetic, and influential. By detecting the effects of vacuum energy, science has uncovered a subtle but powerful aspect of reality, one that operates silently yet shapes matter, forces, and the evolution of the cosmos itself. In the end, the experimental evidence leaves little room for doubt. Vacuum energy is not a theoretical artifact or a philosophical idea. It is a measurable feature of the universe, confirmed by precise experiments and consistent observations. Empty space is not empty. It acts, it influences, and it leaves traces wherever careful measurement is made. Through experiment, the invisible has become undeniable, revealing that the deepest layers of reality are far more active than they appear. The realization that zero-point energy reshapes our understanding of reality and the universe represents one of the most profound intellectual shifts in the history of science. It does not merely add a new concept to physics, it forces a redefinition of what existence itself means. For much of human history, reality was understood in terms of solid objects, empty space, and clear separations between something and nothing. Zero-point energy dissolves these boundaries. It reveals a universe where emptiness is active, where stillness is impossible, and where reality is defined not by static being, but by continuous becoming. At the heart of this transformation is the collapse of the classical idea of nothingness. Classical thinking assumed that if all matter, radiation, and heat were removed, what remained would be absolute emptiness. This notion shaped philosophy, religion, and science alike. Zero-point energy overturns this assumption completely. It shows that even when everything removable is removed, something remains. Space itself carries energy, motion, and structure. The vacuum is not a blank canvas, but a living foundation from which all physical phenomena emerge. This changes how reality is defined at the most basic level. Reality is no longer built from objects placed within space. It is built from fields and fluctuations that give rise to objects. Matter becomes secondary, an expression of deeper processes rather than the fundamental substance of existence. In this view, Particles are not the building blocks of reality, but the visible ripples on an underlying sea of energy. The universe is less like a collection of bricks and more like a continuous ocean of motion, where stable patterns give the illusion of solidity. Time itself takes on a different character under this perspective. Classical intuition often imagines time as a neutral flow against which events occur. Zero-point energy suggests that even in the absence of events, activity continues. There is no moment of complete stillness. At every instant, quantum fluctuations are occurring. This implies that time is always filled with change, even when nothing appears to be happening. The universe never pauses. It is always in motion, even at its quietest. This realization also reshapes the meaning of stability. Stability is no longer the absence of motion, but the balance of motion. Atoms are stable not because they are frozen structures, but because their internal quantum activity settles into allowed patterns. Planets follow stable orbits not because space is static, but because dynamic forces reach equilibrium. Even the apparent permanence of physical laws may arise from deeper fluctuations that average out over time. Stability becomes an emergent property, not a fundamental one. Zero-point energy also transforms how causality is understood. In classical thinking, every effect has a clear cause. In the quantum vacuum, fluctuations arise spontaneously, constrained by probability rather than direct causation. This does not mean reality is random in a chaotic sense, but it does mean that causality is subtler than once believed. Events can be influenced by background activity that has no single identifiable source. The universe contains an element of spontaneity built into its foundation. This has deep implications for cosmology. The origin of the universe has long been framed as the ultimate question. How did something come from nothing? Zero-point energy reframes this question. If empty space already contains energy and structure, then the emergence of a universe does not require creation from absolute nothingness. Instead, it may arise from fluctuations within a pre-existing quantum vacuum. While such ideas remain theoretical, they are grounded in known physics. The universe may be a natural outcome of the properties of space itself. The fate of the universe is also affected by this understanding. If vacuum energy permeates space, it influences cosmic expansion. The accelerated expansion observed today suggests that empty space is doing something active, pushing galaxies apart. The long-term evolution of the cosmos may depend more on the behavior of vacuum energy than on the matter within it. In this sense, emptiness, not substance, may determine the ultimate destiny of everything that exists. On a human scale, zero-point energy challenges everyday intuition. Humans experience the world as solid, quiet, and stable. Zero-point energy reveals that this experience is a coarse approximation. Beneath the surface of every object lies relentless motion. The chair you sit on, the ground beneath your feet, and even your own body are sustained by quantum activity that never rests. Reality is not what it seems at first glance. What feels solid is supported by invisible vibration. This realization does not undermine the reality of human experience, but it deepens it. It shows that the familiar world is an emergent layer resting on a far more dynamic foundation. The everyday and the extraordinary are not separate realms. They are connected by continuous physical processes that operate across scales. The quantum vacuum is not distant or abstract. It is present everywhere, including within the matter that makes up human bodies. Zero-point energy also reshapes the boundary between physics and philosophy. Questions that were once purely metaphysical, such as the nature of nothingness or the origin of existence, are now informed by empirical science. Physics no longer merely describes how things move. It informs what it means for something to exist at all. The vacuum, once dismissed as empty, becomes a central character in the story of reality. This shift affects how knowledge itself is understood. It demonstrates that human intuition, shaped by everyday experience, is not a reliable guide to the deepest truths of nature. Reality operates according to rules that can seem counterintuitive, even paradoxical. Zero-point energy teaches humility. It reminds us that what feels obvious may be wrong, and that understanding often requires abandoning deeply held assumptions. The concept also influences how limits are perceived. Classical thinking imagined that with enough control, systems could be made perfectly still, perfectly isolated, perfectly predictable. Zero-point energy imposes a fundamental limit. Perfect stillness is impossible. Perfect isolation does not exist. Perfect prediction is unattainable. These are not technological shortcomings, but features of reality itself. The universe has built-in uncertainty and motion that cannot be eliminated. At the same time, this restless foundation enables creativity and complexity. Without fluctuations, there would be no variation, and without variation, no structure could form. Zero-point energy provides the raw dynamism from which patterns emerge. Galaxies, stars, planets, life, and consciousness all depend on a universe that is not perfectly uniform or static. The same fluctuations that challenge predictability make existence possible. The reshaping of reality through zero-point energy also affects how science progresses. It encourages a shift from thinking in terms of objects to thinking in terms of processes. Instead of asking only what things are, physics increasingly asks how patterns arise, persist, and change. Reality becomes something that happens rather than something that simply is. The universe is an ongoing process, not a finished structure. This perspective also influences future theories. Attempts to unify quantum, mechanics, and gravity often rely on the idea that spacetime itself may emerge from deeper quantum processes. If space and time arise from fluctuations and entanglements, then zero-point energy is not just a feature of the universe, but part of its origin. The vacuum may be the source from which spacetime itself is born. The emotional impact of this realization should not be underestimated. For some, the loss of absolute emptiness can feel unsettling. For others, it is deeply inspiring. The idea that the universe is alive with activity, even in its quietest moments, offers a vision of reality that is rich, interconnected, and dynamic. It suggests that existence is not a fragile exception carved out of nothingness, but a natural expression of deeper principles. Zero-point energy also invites a reevaluation of humanity's place in the cosmos. Humans are not isolated observers standing apart from an empty universe. They are participants in a vast, vibrating system. The same quantum energy that fills space also shapes the atoms in the brain and the signals that give rise to thought. Consciousness itself emerges within a universe that never stops moving at its core. In reshaping our understanding of reality, zero-point energy does not provide simple answers. Instead, it opens deeper questions. What is the true nature of the vacuum? Why does it have the properties it does? How do its fluctuations give rise to the laws of physics? These questions drive modern research and ensure that the study of the vacuum remains central to future discoveries. Ultimately, zero-point energy teaches that reality is more subtle, more active, and more interconnected than classical thinking ever imagined. The universe is not built on emptiness, but on energy that cannot be removed. Stillness is an illusion, permanence is provisional, and nothingness is never truly nothing. By revealing this, zero-point energy reshapes not only physics, but humanity's understanding of existence itself. It shows that the deepest truth of the universe is not silence or void, but quiet, ceaseless motion underlying everything that is.